Hello and welcome to today's video. So on the workbench today we have an Evnetics Soliton1. I believe that's how you pronounce that. And it's in for repairs. The customer has already replaced a bunch of components. I'll go over that in a second. But first off, shipping. If you're shipping me these motor controllers, these weigh a lot. Pack them really good. See, we've got some damage here. It looks like, you can see how that's bent compared to the other screw. It looks like it took an impact this way and it cracked the fan shroud pretty good. When I open up the box, you've got little plastic bits from the fan floating around in there. That's not good. Just pack them really good. These things are really heavy. The package handlers just kind of drop them. So, other than that, like I said, the customer's tried to fix it already. He's replaced the IGBTs, a couple isolated power supplies, capacitor, 2 opto isolators, and I'm not 100% sure what that is, but given the fact that it is a 5-terminal device, it's either an op-amp or a comparator. So they've been trying to fix it. It's in for me to take a look at because they've replaced all of these parts, and it's giving a saturation error. And so yeah, I can show you. I like it when the customer sends me the bad parts too, because then I can kind of get my failure mode analysis going and figure out what's going on. So if we fire up the meter here, I'll show you that these are in fact, this one's definitely dead shorted. They've conveniently put the schematic here on these units. These are IGBTs, insulated gate bipolar transistors. So normally you'd have it in H-bridge configuration. That's why you have 2 half bridges. Normally they're drawn the other direction, but essentially pin 3 would be your high voltage, and then pin 1 goes out to your motor, one side of your motor, and then pin 2 would be your ground. Same over here, high voltage ground to the motor, and then you would turn on like that MOSFET or that IGBT. And that IGBT to go one direction, you turn that IGBT or that IGBT to go the other direction. You would never want to turn them both on simultaneously up to down. And that's apparently what happened here. Something failed and we got a dead short between everything, and it popped. So the one is definitely dead. Like this one is definitely a dead short. This other one looks like it's okay because it's reading 0.3 volts that way. So we're just reading the body diode. It's open the other direction, and like this one's dead shorted. Now the other side looks like it's also good. So same with this one. So it looks like we only lost one of the 4 IGBTs. However, after saying that, there is something funky going on because the, I don't know if I can do it, but the measurement on the gates is kind of weird on this one. So I'm pretty sure that we had something else. Like even though this one's not dead shorted like this one, there's something funny going on the gate because it actually has a connection to, I think one of the, what is it, the collector? Yeah, this is just really, it's weird. So I'm pretty sure they are both dead. So yeah, I can't check these. They apparently lost some pins when he unsoldered them. And they broke off inside, so I can't check to see if the outputs were shorted on those. But we'll just assume that those are bad. And the opto isolators, the LED side looks okay, but then the other side is just blown open. So yeah. So the error that he's getting is a saturation error, and a saturation error on IGBT is usually what is used to detect that there's too much current flowing through it, or that it's shorted, or that it's open. You get a lot of information, and what you do is you actually measure across from pin 1 to pin 3 if this guy's on, or from pin 1 to pin 2 if this guy's on. And that allows you to essentially measure the voltage that's dropping across here. And by looking at that, you can tell what's going on. I've got the data sheet. Let me turn off the light here. Here we go. I got the data sheet pulled up for this IGBT. So they're 600 volt. They claim to be 800 amps max, but you probably wouldn't run them that high. But yeah, if we scroll down to all the data, this is one of these graphs. There we go. So this graph tells us how much voltage is going to be across the collector and emitter based on how much current. So if you've got your system current limited to say 400 amps or so, or wherever you're actually want to be running, you should never get more than 2 volts across there. So you'd have a little comparator measuring that, and if we went say a little bit above, then we would trip and say, oh, we're saturated, we got a saturation error. The other thing you can do is, if the IGBT, I'm going to keep calling them MOSFETs, but if the IGBT is shorted, you would see 0 volts across there no matter what. And so you can usually have like a window comparator that will detect if it's shorted. If you get full stack voltage across, then you have an open circuit. So usually you have like a little comparator window. I suspect that I would assume, I don't have the schematic for this drive, I would assume that there's some kind of comparator going on. Those are the 3 states that you can learn about your IGBT based on that graph. So essentially, if your 100 amps is going through, you should have about a volt drop across there. So you should be able to measure 1 volt. If you're doing, it starts getting, they diverge out here, but if you're current limited, I mean, even if you tell it that you should be going, 600 amps, you should never have more than 2.5 volts, even when this is up at 150 degrees. And you'd know what your gate voltage, your gate driving voltage is, so you'd know what your curve looks like, so you can fill that in and get those parameters. So it's a pretty simple way to detect if there's a short circuit. And that's what saturation error is. It's just that it thinks that there's a short circuit. So yeah, the fact that the IGBTs have been replaced and you're still getting that error means that something blew up that circuit, that component. So I've already taken all of the screws out, and this is what it looks like on the inside. It is, I mean, this is all machined aluminum. This thing's a beast. I mean, just the amount of weight here is just incredible. And even the back cover, which I thought would be the heatsink, which I thought was weird that the fans are on the other side, is all milled out. And that's out of a single piece, and it looks like even this, I really hope this is cast and then machined. Oh, let me turn the light back on. There you go. I really hope that this is just a casting and then it's machined, but I'm not sure. If this was actually machined from a single piece block of aluminum, that's got to cost a fortune. That's crazy. But anyways, enough about the manufacturing of it. Yeah, so I haven't powered it up yet. But we could go over the kind of the main components. Everything that I need to get to is kind of underneath. So we got a control board. We got a WizNet, which is kind of neat. This is a hardware TCP stack, so that the micro doesn't have to do Ethernet. It can offload it to this guy. And microcontroller, it's pretty simple. Little board. This goes out to all the I/O here on the front, and this Ethernet jack goes to this, which is Ethernet jack. And we've got a couple sensor wires here. This would sense if there's 2 contactors down in there. You can kind of see the other one, whether or not those have closed for the precharge. Assuming there's precharge, and then these 2 wires look like they go down to actually control the contactors, because you can see looks like it's the same wire. And what else? Oh yeah, so we'd be measuring between the 2 to measure for the precharge. So there's 3 wires there. This is all the I/O to the front. I already mentioned that. And then this is your current sensor, which interestingly only goes through 1 leg. Like they've cut a slot in here. You can see it's too wide to fit, so they're just measuring the current through 1 side. And I would assume that's symmetric, and they just multiply by 2 in the software. And then the board that we're interested in, this then goes down, flat flex cable goes down to the this would be your PWM signals to the gate drivers. And this cable here looks like it's a temperature sensor. Goes down to the bottom. And but this is what we're interested in, is this board down here, which is the gate driver board. That would also have the comparators that we're looking for, or op amps, the window comparator, to do the saturation detect. So before I power it up, I think I just want to take it apart and get down there and see if we can't find anything that's messed up on that board. Just visual inspection, see if anything's popped. You can just diode check, because we're going to be looking for something that's going to be across the some kind of sense circuitry that's going across the collector and emitter on these guys. So yeah, that's what I'm planning on doing. So start taking that apart, take lots of pictures, and hopefully we'll figure out what's going on. Thanks for watching. Bye.